Hey, Precalculus, we're moving on to chapter 12. I got a couple more things that I'd really like to talk about before juniors take that SAT, or I know some seniors have the opportunity to retake it. I don't think a whole bunch of you are presently, but sequences and series, this is definitely something that shows up on just about every standardized test, so definitely want to cover this. We're going to start today. We're going to take 2 days on section 12.1, so you might as well go to your notes right now and write this is day 1. I could actually turn this into 3 days if I really needed to stretch it out, but we're not in that kind of a mood right now. So here we go. This is what sequences are about. You've seen things like this on, some of those standardized tests that you've taken in your history before. Fill in the next 3 blanks for each sequence of numbers. Now, what you normally try to do with this, which is a little bit of a mistake, is you normally try and notice a pattern from this number to this number to this number. That's what you normally try to do. What I want to tell you is these are y values from a function. Okay? They are y values from a function. Now I can pull that off with this. Look, 14, to get to 17, I add 3. To get to 20, I add 3. I really should have put another number in here so it was obvious what the pattern is, because sometimes a pattern will stick together for 2 numbers and a different pattern will also stick together for 2 numbers and you can't tell which one it is. In this one I did intend this to be adding 3 from number to number. But when you have sequences that you can fill in numbers like this that quickly, that leads you into this real false sense of security that that's how all of these go, and there is definitely a different strategy to this kind of thing. This is a function and you don't even see it. Like, you don't see the x values at all. All you're seeing are the y values, and you don't even recognize their y values. You just think we're playing a little numbers game here. Okay, 127, 1/9, 1/3. What is happening here is I am dividing this number by 3. Right? What that means is I'm multiplying the fraction by 3. If you take 1 over 27 and you multiply it by 3, the 3 and the 27 cancel. That's why it looks like you're dividing. If you take 1/9 and you multiply that 1/9 times 3, the 3 and the 9 cancel, and that's why it looks like you're dividing by 3. We're not dividing the we're not dividing the denominator by 3. We're multiplying the fraction by 3. So multiply by 3 again and I get 1. Multiply by 3, multiply by 3. In that scenario, there's both of these first two. There's a real simple math thing that is happening to each, what we're going to call a term, that's constant. So you could just generate more numbers from in that capacity, from one number to another number with the same kind of math. Now, this next one isn't like that. It's not like that at all. This next one has to do with x's and y's. See, if I add 3, and then I try and add 3 again, that doesn't play out. Certainly can't add 3 and get 16. If I multiply by 4, this works, but multiply by 4, this does not work. And then your brain starts to mess with it. Well, maybe it's every other one because you multiply by 4 and you get here. That's not what's going on. These are perfect squares. The next one is 25. The next one is 36. And the next one is 49. Those are the perfect squares. Now I'm going to point out to you with XY charts why these are actually functions and not just playing a little game with numbers like a puzzle. This first one we had 14, 17, and 20. Now look, we had 23, 26, and 29. And you would stop even thinking about these and just keep adding 3 if I asked you to do it all day. But look, this is the first term, so I'll put a 1 there. This is the second term, so I'll put a 2, a third term, a fourth term, a fifth term, and a sixth term. Those numbers can get paired up with their term number. Okay, so we're going to call this a term sooner or later in here. But this is the term number. Okay? Now look, we added 3 each time, right? Isn't that what we were doing? We're adding 3 each time. If you, let's see, how can I put this? I'll get back to that. I'm just gonna move on. We'll do the next one. Put down a 1, 2, 3, 4, 5, 6, and then a 1, a 3, and a 9. They are pairs of numbers. Even though you don't see the x, You just see the y value. You see the resulting, the ones from the range. The x ones are there. There's just the number of the term. Now look at this one as plain to see. So we decided they were the perfect square. So it's 25, and then it's 36, and then it's 49. Now watch this. I'm going to put 1, 2, 3, 4, 5, 6, and 7. Now look at every one of those x values and square it and see if you don't get that y value. So there is a math connection here. It's x squared, isn't it? Take each one of those numbers and square it. So that x goes in here, gets squared, and becomes the y value. True? Now there's something that could happen here. Here's a hint. I added 3 every time, right? For each one of these, multiply this by 3, multiply 5 by 3, you get 15. What would you have to add? 11. Multiply by 3, you get 12. What would you have to add? 11. Multiply by 3, you get 9. What would you have to add? 11. Multiply by 3, you get 18. What would you have to add? 11. This one is 3x plus 11, isn't it? So there's an actual formula that's generating these numbers. To you, it just looks like, hey, add 3 and keep going and let's get out of here. But there's more going on behind the scenes here. All right, definition of sequence. A sequence is a function whose domain, the numbers we put in for x, is the set of positive integers. Okay, that's the definition. Now, this isn't in the book. I'm just going to say that sometimes they start at 0 and it throws you guys, and I just want to put that in there. Okay, a sequence, which is right here, that's the sequence. It's the result of a function whose domain is the positive integers. What are positive integers? 1, 2, 3, 4, 5, 6, the whole numbers, right? The counting numbers. So a sequence basically generates a list of numbers as a result of using the following as x values or input numbers. This is what we do. We put in 1, 2, 3, 4, and on in for x. We get a bunch of y values, and they are what you see as a sequence. Okay? There's page 1. Let's go on to page 2. Earth-shattering for you, I know. Nobody bothered to tell you that those are just y values, and there was an x value behind, did they? I'm here to help. Okay, now I'm going to do some review right here. This is about functions, stuff that we've already studied, stuff that you know. Ready? Functions are described in several ways, but the most important that we have dealt with this year are an equation. We've seen plenty of those. Describe a function with an equation, right? A set of points with an XY table. That was really important earlier on in your math career. Wasn't algebra, like your first class, wasn't it all about just finding points and plotting them to see what the graphs look like? You don't need that anymore. You see an equation, you know what it looks like now. You're so grown up. I'm so proud. And then a graph. We have spent a lot of time in Algebra 2 and Precalculus graphing those equations and manipulating those equations, yes? Okay, describe the parent function for a quadratic in all 3 ways listed above. An equation, a set of points, and a graph. Ready? F of x equals x squared. There's your y equals x squared parabola. If you put in a -2, you get 4. -2 squared is 4, correct? -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. There you go. There's a set of points that describe quadratic behavior. And we're supposed to graph this thing. Well, this is so tiny. I'm going to skip a line and have this be a 1. I'll skip a line and then make a 2, skip a line 3, skip a line 4. And so the end of this on the right is 5. You know, scale it by skipping a line. And then what will we do? Same thing here. We'll go, that's 1, that's 2, that's 3, that's 4. And if I skip every other line, I'm up to 5. Okay? I'm going to graph the points that I have. -2, skip a line, and then get to -2. And then we're going up to 4, so that's all the way up here. -1, 1 is right there. 0, 0, 1, 1, and 2, 4. And then I always connect the dots, so, right, with the function. When the domain is all real numbers, you connect the dots. When the domain is just the integers, you don't. You just leave the dots. So that's going to be a difference here. When we graph this, it's just dots. No connecting the dots because the domain is limited. A sequence can be described in the same 3 ways, but each is a little different. Instead of function notation like f of x equals the square root of x, We use this. Ready? Watch. A sub n is equal to n to the second power. Like if we were doing that one, that's how we would write it as a sequence. A sub n, that's a subscript n. And we use that specifically. This notation specifically suggests that we only use integers for the domain. No fractions, no decimals. You put in 1, 2, 3, and 4. You don't even use negatives or 0. Just 1, 2, 3, 4. Instead of an entire chart, like we saw on the first page, we just list the y values. Instead of an entire chart, that's all we do, is I just give you 4, 1, 0, 1, 4. That's all I give you. Look at the other page. Let me go backwards. That's all you were given is just the y values, right? But you can tell they are clearly hooked up with x values and their y values, and they're part of a function. I could graph them. I could see a pattern. In fact, if I did graph them, I would see a linear pattern, right? Okay. Instead of the entire chart, when we talk about a sequence, it's just, I'm trying to get in the middle of the screen there. Sorry for you. Sorry about that. Just the y values. And what do we call them? We call them terms of a sequence. Now, when you graph a sequence, the pattern shows up as a group of dots. Do not connect the dots when you're not using x values in between the integers. Don't connect the dots. So here we go. I'm going to go a sub n is equal to n squared. And I'm going to do my best little sketch of a graph here. There's 1, 2, 3, and I'm going to run out of room, so I'm going to do this kind of smaller. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Put in a 1, you get a 1. Put in a 2, you get a 4. Put in a 3, you get a 9. That's it. I don't connect it. That's just gives you an indication of what the drawing looks like. I don't have any points in between those, so I don't connect them. Page 3. You're doing great, by the way. I'm really proud of you guys today. Dream team. All right, when we write out an expression like a sub n is equal to 2n minus 1. If we're going to write out an expression that actually tells you how to generate terms of a sequence, what I would do is I would put 1 in there, then I would put 2 in there, then I would put 3 in there, then I would put 4 in there, and I would generate terms of a sequence. They're y values, they're range values, but I collect them and call them terms of a sequence. We refer to it as a formula for the nth term. That is an nth term formula. I got to put this in there. The old author liked to call this an explicit formula. And I really like that term instead of calling this a formula for the nth term. But I'm okay with either way. Sometimes they say they'll refer to this as the general term. So the formula is going to be the general term. So specifically, you could put a 1 in there and get the y value for the first term. Or you could put a 5 in there and you would get a value and it would be the 5th term. And this just kind of represents the general term. So that's what that means. I just did air quotes in the camera, and I'm not really sure why. Okay, what this author does, which I find really weird, is he puts the whole thing in brackets. I've never seen a math person do this before, and I want you guys to see the same kind of stuff you're going to see on my math lab. So I'm going to do it, but I just think it's weird. This is what a normal person would write. If they're just going to write this equation out. My equal sign turned into my denominator, little fraction bar there. Sorry about that. That's what a normal person would write. But this author has decided to put brackets around it, and I got no idea why. But here we go. We're going to do this a few times. Given that formula, write out the first 6 terms, and then graph them. Okay. Well, here's my formula. N minus 1 over 1 is my general term. So I'm going to put in a 1 first, and I get 1 minus 1 over 1. Then I'm going to put in a 2. I get 2 minus 1 over 2. Then I put a 3 in for n. I get 3 minus 1 over 3. I'm generating terms, which are technically y values, by putting in x values of 1, 2, 3, 4, 5, and 6. So I get 4 minus 1 over 4, 5 minus 1 over 5, and 6 minus 1 over 6. Simplify those, and we get the first 6 terms of a sequence. They are 0 over 1, 1 over 2, 2 over 3, 3 over 4, 4 over 5, and 5 over 6. Probably easier to graph those if they were decimals, wouldn't you say? I'm going to take a shot at it, though. So this time, since, look, the biggest value I get, it would be like 1, right? Okay, so I'm going to let's see, I'm going to do this. I'm going to skip 1 and put a 1, skip 1, make it a 2, skip 1, make it a 3, make it a 4, and have 5 out at the end. So 6 would be out here, right? Let's just go halfway up and call that a 1, and the rest of it would be a 2. So I'm going to scale it that way just so that we can graph it and see it, okay? When I put in a 1, I got a 0, I have the point 1, 0. When I put in a 2, I got a 1/2, so I go 2, and then 1/2 is going to be right there. When I put in a 3, I got 2/3, so let's see, if that's 1/2, 2/3 would be just a little bit past that. When I put in a 1, 2, 3, 4, I got 3/4, so, wait, I missed one. Sorry, when I put in a 3, I got, how did I screw this up? So I got 1, 1/2, 2, 2/3. No, I'm okay. This would be 3, wouldn't it? 1, 2, 3. Oh, that should have been 1. It should have been at 1, 0. You guys see what happened? Okay. I just tried to spell loser and I spelled it wrong. Tried to spell loser and I spelled it wrong. Oh dear God, I can't take it anymore, people. I can't take the school year anymore. Pandemic. Pandemic. Okay, here we go. 1, 2, 3, 4, 5, 6, and we'll say that this is 1 right here. So ready? This would be 0.5, and then I'll go 1, 2, 3, 4, 1, 2, 3, 4. Now I've got little spots for every 10th. So I'm not going to put anything at the origin because I didn't put 0 in for n. That's how I screwed this up the first time by putting some at the origin. I'm a lorer. So I put in a 1, I got a 0. I put in a 2, I get 1/2. It's right there. Put in a 3, you get 2/3. That's 0.67. That's going to be right there. Put in a 4, you get 3/4. So this goes up to 0.75. 4/5 is up to 0.8. 5/6 is up here somewhere. So there's your dots. It's not a perfect graph, but you know, what do you expect? I'm a lorer. All right, let's list the first 6 terms of each sequence. This should be easy. Put in a 1. 2 times 1 plus 7. Put in a 2. 2 times 2 plus 7. Put in a 3. 2 times 3 plus 7. That one doesn't look right. Put in a 4. 2 times 4 plus 7. Put in a 5, 2 times 5 plus 7. Put in a 6, 2 times 6 plus 7. You just substitute 1 in for each one of them. And look, 2 plus 7 is 9. 4 plus 7 is 11. 6 plus 7 is 13. 8 plus 7 is 15. And now you see a pattern, right? Instead of doing the x to y math, you could now say, hey, I'm adding 2 every time. These are going to be 17 and 19, right? 2 plus 5 is 10, plus 7 is 17. 2 plus 6 is 12, plus 7 is 19. There you go. Look at this mess. What a hot mess. Zoom in on that if you can. 1/3 times -2 to the n minus 1. Don't get freaked out. Just write what you see. I'm going to put a 1 in for n. So I have 1/3 times -2 to the 1 minus 1 is 0. Yeah? Okay, for the second one, it'll be 1/3 times -2 to the 2 minus 1 is 1. For the third one, 1/3 times -2, I'm putting in a 3 for n, and 3 minus 1 is 2. Now look, you can see the pattern, and your brain can relax, and it's not as bad as it looks. So for the next one, I'll put in a, let's say I put in a 1, a 2, a 3, this will put in a 4, and so I get 1/3 times -2 to the third. You can see an obvious pattern here. I got 2 more to go, and they're going to be 1/3 times -2 to the 4, and 1/3 times -2 to the 5. Right? Don't freak out because the notation looks scary. Just write what you see. -2 to the 0 is 1. This first term is just 1/3. Right? -2 to the 1 is -2. And -2 times 1/3 is -2/3. -2 squared is going to be a positive 4, and it's over 3, so 4/3. -2 to the 3 will be -8 over 3. -2 to the 4, 2, 4, 8, 16, positive 16 over 3. And the last one, -2 to the 5 is going to be -32, and it's over 3. Now again, just like in the last one, where you could have picked up on a pattern and said, hey, I'm adding 2 every time, and made it a little more efficient. You could have run with it, right? I mean, I'd rather see you show the work so it's obvious you know what you're doing. But look at the pattern here. They're all over 3. And what's happening here? I'm multiplying by -2 every time. Yeah? It's because I'm multiplying by -2 to some power. I'm multiplying by -2 every time. And obviously they switch positive, negative, positive, negative. So forget about putting numbers in. Wouldn't the next one be positive 64 over 3? Right. Okay. N squared plus 3. Put in a 1, we have 1 squared plus 3. Then we have 2 squared plus 3. Then we have 3 squared plus 3. 4 squared plus 3. 5 squared plus 3. And 6 squared plus 3. There's some students who just love this kind of stuff. They just see the patterns and they just go. And it's almost like your brain can disengage. You don't have to think that hard. You just write what you see and just do stuff. And you circle answers and feel good about yourself. Some math students are like that with this. Some people look at the notation and just get terrified. I think everyone could land somewhere in the middle of that. 1 plus 3 is 4. 4 plus 3 is 7. Let's see, 9 plus 3 is 12. 16 plus 3, let's see, 16 plus 3, 19. 25 plus 3 is 28. And 36 plus 3 is 39. There's your first 6 terms for that one. Okay, terrifying, right? That's absolutely terrifying. I've got a -1 as a base raised to an exponent that's an expression, n plus 1, and then it's times 2 over n, there's a fraction. Dear God, what is going to happen to us? Just write what you see. -1 to the, if I put a 1 in there, 1 plus 1 is 2, and it's times 2 over 1. All right, that's my first one. We'll simplify it later. Let's just write all 6 of them. The second one, -1. When I put in a 2, 2 plus 1 is 3, and it'll be times 2 over 2. When I go to do the third one, it'll be a -1. I put in a 1, I put in a 2, I put in a 3. 3 plus 1 is 4, and it'll be times 2 over 3. Now look at the patterns. There's a -1, that's going up 1. This is going up 1. Yeah? The 2 stays the same. So I'm just going to fill out the other 3. -1 to the 5 times 2 over 4. -1 to the 6 times 2 over 5. And -1 to the 7 times 2 over 6. There's my 6 terms. I stopped putting numbers in there because I recognized the pattern. Don't jump too early at recognizing patterns, guys, but it can help you out a bit, as you can see. -1 squared is 1. This is 1 times 2. My first term is just 2. That with a 1 put in it is just 2. -1 to the third is negative times 1. This will actually be -1 for the second one. -1 to the fourth is positive times 2/3, so 2/3. -1 to the fifth is negative times 2/4 is -1/2. -1 to the sixth is positive times 2/5 is 2/5. And -1 to the 7 is negative times 2/6 is -1/3. Hey, there's your 6 terms. Now look, some of it looks scary, the notation's weird, but honestly, you're just putting x's in and simplifying. It's all you're doing. That's all you're doing. There's a lot of background stuff for us to talk about, but as intimidating and scary as that looks, all you're doing is putting in numbers and simplifying, and you are good at that, whether you believe it or not. All right, what do we got next? I got 2 more pages. This is a long video today, sorry about that, but introducing sequences, there's a lot to be said. Let's see. The calculator can generate terms for us in a couple of ways. True. In your regular function mode, which I am not in presently, so let me go find function mode and hit clear. There's my calculator. You can hit second and the stat button to go to the list menu. Now you may not have ever used this before. There's my stat button right in the middle there. We use that in AP stats all the time. And then we're going to go to the list button. Ready? Second and list. Now there's lists. We use those in stats all the time also. But I want to go over to OPS, the operations menu. So I'm going to scroll over to OPS. And then number 3, I'm going to find the sequence menu. I'm going to hit enter. So I'm going to go down to number 5. I'm going to hit sequence. And I get a pop-up menu. Some of you guys may not. So what I'm going to do in number 4, if you don't get a pop-up menu and it just goes to your home screen, these are things you have to fill in. You have to put commas in between them. Okay, so I'm not going to put anything here yet. I'm going to tell those of you who don't have that pop-up menu what you have to put in. You have to put in an a sub n formula, like the ones that we were just generating terms from. You have to put x, saying I'm using x as my variable, so hopefully you typed in using the x button. You put in a starting number, that's usually going to be 1, n equals 1, right? You put an ending number, whatever you, we were using 6, right? We were using 6. And the increment, that will always be 1 because we put in integers, so I'm going up by 1. All right, so let's go and find the first 6 terms from 2n plus 7. I want to go back for just a second so you see it. 2n plus 7, that's this first one. 9, 11, 13, 15, 17, and 19. Okay, I'm going to put this in the calculator, and the calculator will generate them for me. Really cool. My expression, 2n plus 7. So I go 2, I hit the x button, and it says x instead of n. We're going to change modes in a minute, and you can get an n in there. We'll just leave it as x. What variable is it? Just hit the x again and tell it, yeah, I'm using x as a variable. What do I start with? I start with the integer 1. I end with the integer 6. And my step or my increment is 1, meaning when I'm done with number 1, I go up 1 to get to number 2, then I go up 1 to get to number 3. That's what that means. Okay, I'm going to hit paste, and those of you who don't have that pop-up menu, that's what you need to type in when you hit sequence. It'll open parentheses for you. You got to type in 2x plus 7, and you have to hit a comma, and the comma is right above this 7 here. And then you hit the x and a comma, a 1, a comma, a 6, a comma, and a 1. So you got to know what to put in there. That's why the pop-up menu is helpful. But look, I'm going to hit enter, and look what it does. 9, 11, 13, 15, 17, and 19 generated the whole thing for me. It was really nice of it, wasn't it? Okay, that's one option. In sequence mode, okay, we're going to hit the mode button, and we're going to change this thing, like going from radians to degrees. But this time, we're going to go from function mode to sequence mode, and I'm going to guess that's something that none of you have seen before. So look, I'm going to hit the mode button. I'm in degree mode, but I'm going to go below that one to where it says function. Parametric, Mr. Smith and I are going to try and see if we can get time where we can talk about that before the semester's over. Polar mode, I would love to do some polar mode stuff with you. That's the last on the priority list, though. And then sequence mode. All right, I'm going to hit enter, and my whole calculator just changed. Are you ready for this? You want to see something crazy? I'm going to hit y equals. Ready? Y equals. Look how different that looks. I mean, look how different that looks. It's crazy. So it's no longer functions. You don't put x's and get y's. They have different notation. So you should have a 1 at the top for the minimum. So let's see. Hit mode, hit function, hit sequence. Hit y equals like I just did and see how different it looks. Look, different. The minimum should be 1 because we're going to start with 1 every time. So that the sequence generates terms starting with n equals 1. Then type in the a sub n formula, like that 2n plus 7, for u with n in parentheses, okay? It's right there. There's a u with an n in parentheses. And so, look, I'm just going to type it in, 2n plus 7. So watch what happens now. I hit 2. When I hit the n button, I know my fingers you can't see. When I hit this button, it's not going to be an x now. It's an n. Look at that. And then what was it? It was supposed to be plus 7. So I hit plus 7 and then enter. So I have now, just as if I put a function in y equals to graph a line or whatever, I just put a sequence in my calculator. For now, we're going to ignore U1 and U2. I may not get back to those. We'll see tomorrow. You can view terms now in your table or by looking at a graph. And when it graphs these points, you guys, it's not going to connect them. It's going to leave them as dots. So let's do the table first. Okay, your table is right here, and your table set is right here. I'm very sure that an algebra teacher worked with you with these before, but it's probably been a while, right? So the first thing I want to do is I want to go to the table set. So I hit second and window, and we're going to set up how it generates the table. I want the table to start at 1 because I want it to start at n equals 1. And I want the change in the table to be 1 just like I wanted it to be 1 up here with the increment change. I don't want to have to ask it to give me values. I could if the question asked for like the 100th term or whatever, but I'm just going to generate them for now. Okay? Then, as soon as I go to the table, I'm going to get a list. Ready? I'm going to hit second and graph. I'll go to the table, and look, it shows them as XY points. There's 1 through 11. There's the 9, 11, 13, 15, 17, and 19 that we saw, and then there's even more. And I can scroll down, and I can get as many of these as I want. Or if you were in ask mode, I would put in an n, and it would give me the y value, right? So that's how the table works. So you set the table set to start at 1 and to change by 1. You leave it on auto. Let's go find the first 6 terms for n squared plus 3. Okay, first 6 terms for n squared plus 3. So I hit y equals, and I go n squared plus 3. Then I'm going to hit my table, and I got to scroll back up to 1 because it didn't reset it. As soon as you start scrolling, the table set gets changed to wherever you scrolled, right? So I'm going to scroll down until the 1 is at the top like it was. N squared plus 3, 1 squared plus 3, 2 squared plus 3, 3 squared plus 3, and on and on and on. So there's a way to use the table to generate a sequence for you. Now you could also, once this is in for like the y equals kind of thing, you can hit zoom and 0 for zoom fit. And then you trace. Ready? Watch this. I'm going to go zoom. And then it's down past this 9. I'm going to go all the way to zoom 10, but it's just 0 for zoom fit. And look what happens. There's all my dots. And if I want to see them, hit trace and hit to the right, and you'll jump dot to dot. And the calculator at the bottom will tell you the x number, that's your term number, and the y value is your sequence number. So you can just trace and see them all that way. So there's 2 options to use the calculator to do this. All right. Important fact, the nth term formula can be written in multiple ways. It doesn't have to be written in the same way. You can generate the exact same sequence by rewriting things. Ready? Here we go. First 6 terms. So I'm going to go 1, 2, 3, 4, 5, and 6. I'm going to put out my first 6 terms. If n is even, it's just n. If it's odd, it's 1 over n. So this first one will be 1 over 1. The second one is even, so it'll just be n. The third one is odd, so it'll be 1 over 3. The fourth one is even, so it'll just be 4. The fifth one is odd, so it's 1 over 5. And the sixth one is even, so it's just 6. There's my sequence. 1, 2, 1/3, 4, 1/5, 6. It's a weird looking sequence, but it's a sequence. Now look here, I'm going to go 1, 2, 3, 4, 5, and 6, and look at this craziness. I've got b sub n, they're in brackets to make it look even scarier. I think that's what the author's problem is. He just wants to be scary. He hates children. So anyway, b sub n is equal to, put in your term number, to the -1 to your term number. That looks weird. Just write what you see. 1 to the -1 to the first power. Don't even think about it. Move on to the next one. 2 to the -1 to the second power. 3 to the -1 to the third power. 4 to the -1 to the fourth power. 5 to the -1 to the fifth power. And 6 to the -1 to the sixth power. Yeah, raising an exponent to an exponent is weird. That's definitely weird. But look what happens. -1 to the first power is -1. This is 1 to the -1. How do we write 1 to the -1? We put in the denominator, 1 over 1. Hey, look at that. -1 to the second power is just 1. So this is just 2 to the 1. That's 2. Look at that. The -1 to the third is negative, so this is 3 to the -1, which means put it in the denominator, just like that. -1 to the 4 is positive, so it's 4 to the +1. That's not 4, it's -1 times -1 times -1 times -1, so it's just 1. 4 to the 1 is 4. 5 to the -1 is 1/5, and 6 to the 1 is 6. I got the exact same values with 2 different, very different looking expressions, and so I just want you to know it could be written different and describe the same thing. All right, is this the last page? Whoa, my goodness, lots of stuff on here. 4 pages. Did I just say, oh my goodness, like a grandma? Anyway, last thing today. Determining. Determining an nth term formula from a sequence. Guys, this is not easy. Look, I even gave a little... This would be really difficult. I better take a drink of my water here. Find the nth term formula if you're just given a sequence. Just come up with it. Just come up with it. Just in your head. Just look at this and go, oh yeah, I got this. It's a sub n equals 3n minus 1, of course. That's your job. Just look at it and come up with it. Right? Well, maybe you could use a giant hint. Maybe that makes you go, yeah, I quit math. Here's a giant hint. It usually, did I just say here's a giant hint? That's not right. That's not right. It usually helps a lot if you write the terms as pairs with their term number. Pairs with their term number. So look, yeah, I'm going to write the 2, the 5, the 8, the 11, the 14, the 17, and the 20. And looking at them, it doesn't make a whole lot of sense. Other than this, you can see that you're adding 3 every time. And some of you already saw that before you even started. You're like, yep, you're adding 3 every time. So the next one would be 23. If I asked you what the next one is, that would be an easier question. But that's not what I'm asking. I'm asking for this equation. So look, put the term numbers above them. And look at it until you see a pattern. Okay? Think, what math consistently happens to the term number in order to turn it into the term? What math is going on? Okay? It's usually easier if you focus towards bigger numbers. Like the first two are not usually that helpful. So look, what math is going on here? I could go this times 2, and I get 8, and then I have to add 3. But if I go this times 2, I get 10, and I don't add 3. I go this times 2, I get 12, I don't add 3. So that doesn't work. But think about it a little bit. If I multiply by 3, I subtract 1. If I multiply by 3, I subtract 1. If I multiply by 3, I subtract 1. And so looking at the numbers this way, going, how do I turn that x into that y? You are a lot more likely to see it. All right? So I've got some work for us to do here. This is our last page. We're done after this. Write the nth term formula. You guys, I think this first one is easy. We don't need to write the 1 through 6. Look, we got e. The second term is 2. We got e to the 2 over 2, e to the 3 over 3, e to the 4 over 4, e to the 5 over 5, e to the 6 over 6. This one I think is pretty easy. A sub n equals e to the n over n. This is e to the 2, e to the 3, e to the 4, e to the 5, e to the 6, e to the n. This is 2, 3, 4, 5, 6. It's just an n down there. That's it. Just write the pattern that you see. Okay, the second one, I definitely see that the top is 1, right? That never changes, so it's going to be 1. The formula is a constant. It's not 1 to the n. It's not anything like that. It's just 1. What's going on the bottom? I have a 1, a 3, a 9, a 27. It looks like I'm multiplying by 3, but I can't put 3n here because that doesn't work, right? So I'm going to tell you that this is 3 to the n minus 1. I'm just going to say it, and I want you to take a look at that for a second. If I put in a 1, 3 to the 0 is 1 in the denominator. If I put a 2, 3 to the 1 is 3. If I put in a 3, 3 to the 2 is 9. And if I put in a 4, 3 to the 3 is 27. When you're multiplying, it's going to end up being some kind of an exponent. Okay? Number 3, 1, 3, 5, 7, and 9. So I'm going to go up here for number 3, and I'm going to write down 1, 2, 3, 4, and 5. I'm going to go 1, 3, 5, 7, and 9. Here's my XY chart, and you are supposed to figure out what math is happening. What math is happening? Don't look at the beginning numbers, look at the end numbers. What do I do to turn a 5 into a 9? Isn't it times 2 and minus 1? Right? I mean, I'm trying to get through these notes for you guys without taking an hour and a half, so I'm rushing that a little bit, but I think you would have found that. This one is times 2 and minus 1, and so I write it like that. A sub n equals 2n minus 1. This is so easy. I'm not even going to say any words. I'm just going to write it down. Moving on. Well, look at number 5. It's got positives and negatives. Okay, I'm not expecting you to stare at that and just get it. I'm going to show you how you get positives and negatives. Okay, so I'm kind of teaching by doing right now. I'm not expecting you would come up with this. I hope you understand that. I got a positive, then a negative, then a positive, then a negative, but they're all ones. So it's a 1 here. And this is how this works. You take -1 and you raise it to an exponent. We've already seen that today. If I raise this to a 2, I get 1. But if I raise it to a 3, I get -1. Raise it to a 4, I get 1. Raise it to a 5, I get -1. So we just got to figure out how to start this out with being positive. I don't want it to be n because -1 to the 1 would be negative. So I'm going to put n plus 1 here so that when I go to put a 1 in, it's -1 to the 2 and it's positive, and there I go. And then when I put in a 2, it's 2 plus 1 is 3, it's -1 to the 3, that's negative, and there I go. Now look what's going on in the denominator. 1, 2, 3, 4, 5. Isn't that just n? Right? That's how I get those numbers in the denominator. All right, last one. I'm going to go over here to number 6. I'm going to go 1, 2, 3, 4, and 5. Some of the harder ones, I want to write out the actual term numbers and the terms. I didn't do this every time because some of them, especially that one, I thought is so easy. I don't need to write that out. You can see it, right? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. It's just n squared. Okay, but you can always write this out if you're having any kind of trouble, and I really do think that looking at the number helps. Okay, I clearly have a fraction going on. So a sub n is some kind of fraction. Now what's going on in the top? I have 1, I put in a 2, I get a 3. I put in a 3, I get a 5. I put in a 4, I get a 7. I put a 5 and a 9. Aren't these those numbers right there? So what did I have for number 3? I had 2n minus 1. That's what's going on in the top. 2n minus 1. Put this in, you get 2 minus 1 is 1. Put this in, you get 4 minus 1 is 3 in the numerator. Put 3 in, you get 6 minus 1 is 5. And in the bottom, 1, 4, 9, 16, and 25. That's these. So this is just an n squared down there. There we go, you guys. That's only half of section 12.1. We are in a chapter where there's lots of notation things. I think you guys want to stay on top of doing your homework. You want to be real careful with how you write things. Think about how my math lab likes to grade, right? That you got to be real particular. There are a lot of ideas, and I know I went a little fast today, and I did 5 pages, and tomorrow is going to be, something that's kind of similar. But then the next sections after that, we're going to sort of find a groove. We'll hit cruise control. All right, so that's a lot. And so there's a lot of different kinds of problems I could give you. I will try not to overwhelm you with my math lab today, especially since notes went so long. And there's more fun with sequences tomorrow. Have a good day, everybody.